The second concept we're going to look at is how do we calculate the probability of dependent events. Certainly not all events are independent of each other, and one trial could impact the following trial, and that's what we're going to look at here. If the occurrence of the first event does affect the probability of the second event occurring, then the events are called dependent. So dependent means if we have the first trial, it will somehow impact the results of our second trial. An example of dependent event is drawing a card from a standard deck of cards, not putting it back in, and then drawing a second card. So if we don't put the card back in, our chances of getting another card or another probability, our chances have increased because we've gone from a 52 card deck to a 51. So to find the probability of drawing a jack and then a queen, in this situation, we modify the multiplication rule that we looked at. From our previous one, when they're independent, we simply multiply the probability of jack times the probability of queen. But because these are dependent events, we have to modify a bit. Probability of drawing a jack, there are 4 jacks in a deck out of 52 cards. That's the first thing that we want to have happen, so we're going to get the probability of a jack. The big thing here is that we are not putting it back in. It's said to be without replacement. So if you do not replace the card, obviously the total number of outcomes that are possible goes down from 52 to 51. There's only 51 cards left. Now we want to find a queen. Well, the card that we pulled out here was a jack, so it was not a queen. We needed to have a jack pulled out, so we know a jack was removed. That means all 4 queens are still in play in that deck, so there's 4 out of, in this case, 51, because we pulled the jack out. So if we multiply those probabilities together, we can find the chances of getting a jack followed by a queen. The probability of event A occurring, given that event B has already occurred, is called conditional probability. What we're saying back in this previous example is, what's the probability of getting a jack and then a queen? If we already know the jack was pulled out in the first card, followed by a queen in the second card that we pull out. So it's conditional. It depends on what happens to the trial in front of it. This is represented mathematically by these symbols. This is the probability of event B occurring given that we know A has occurred, or simply the probability of B given A. What's the chance of B occurring if we already know event A, such as pulling out a jack, has occurred? This notation is used in the rule for the probability of 2 dependent events. Now we're changing gears from independent to dependent events. Pretty similar, but we make a small adjustment. The 2 events A and B are dependent. The probability that A and B will both occur is a probability of A and B equals the probability of A times the probability of B given A. And again, we can extend this into 3 or more dependent events. So here's the example. We're going to look at this and try to illustrate the idea. A bag contains 12 red, 9 blue, 11 yellow, and 8 green marbles. If 2 marbles are drawn at random and not replaced, what is the probability that a red and then a blue marble are drawn? So here's the framework. What we want to do is we want to calculate the probability of getting a red one and follow that up with getting a blue one. So we want the probability of getting a red marble and follow that up with getting a blue marble. The difference on this problem versus the one that we looked at prior to, we are not going to replace the marble once we draw it out. So this is a dependent event. What we get on that first draw, we will draw a red one out. We're not going to replace it. It's going to impact how many marbles are left in the second time. So first thing we're going to do is we're going to find the probability of, I'm going to use a different color on that. We're going to find the probability of red. Then we're going to multiply it times the probability of blue, given that we know a red one was already pulled out and removed. So let's go back and calculate our each probability of each one of these occurrences. So the first one's the probability of red. Probability of red means we need to know how many possible outcomes there are in our first draw. On our first draw, we know that we have 12 marbles that are red, 9 blue, 11 yellow, and 8 green. Well, that gets us a total out. That's 20, and this is 20, so a total of 40 possibilities. So we have 40 possible outcomes. Of those, how many of them are favorable? Well, favorable means they would be red. That would be 12 out of 40. We take that times the probability of getting a blue one now, given the fact that we know that we found a red one and we pulled it out and didn't replace it. The fact that we didn't replace it now puts us into a mode of only 39 marbles left to draw from. And we know that the one that we pulled out was red. So what's the chances that it'll be blue? That means there are still 9 blue ones left. We didn't pull out a blue one in the first one, it was red, so this is the calculation for our probability. So what we can do is we can multiply these out, reduce them. I'm going to use the calculator just to speed that process up. We're going to take our 12 times 9, that's 108. We got 40 times 39. So we have 108 out of 1560, 108 out of 1,560, and then to speed that up, we can take 108 divided by 1,560, and then we can change that back into fractions. Since we have the tool, we can use the tool to turn that back into, in lowest terms, we have a 9 out of 130. So this one is on dependent events. We have to make that subtle shift in what's going to happen to the number of possible outcomes if we don't replace. They're going to go down. So keep in mind we're looking and evaluating at independent versus dependent.